Area navigation, RNAV, permits electronic course guidance on any direct route between points established by the pilot. While RNAV is a generic term that applies to a variety of navigational aids, such as LORAN-C, GPS, and others, this section deals with VOR DME-based RNAV. VOR DME RNAV is not a separate ground-based nav aid, but a method of navigation using VOR DME and VORTAC signals specially processed by the aircraft's RNAV computer. In its simplest form, VOR DME RNAV allows the pilot to electronically move VORTACs around to more convenient locations. Once electronically relocated, they are referred to as waypoints. These waypoints are described as a combination of a selected radial and distance within the service volume of the VORTAC to be used. These waypoints allow a straight course to be flown between almost any origin and destination without regard to the orientation of VORTACs or the existence of airways. While the capabilities and methods of operation of VOR DME RNAV units differ, there are basic principles of operation that are common to all. Pilots are urged to study the manufacturer's operating guide and receive instruction prior to the use of VOR DME RNAV or any unfamiliar navigational system. Operational information and limitations should also be sought from placards and the supplement section of the AFM POH. VOR DME-based RNAV units operate in at least 3 modes: VOR, en route, and approach. A 4th mode, VOR parallel, may also be found on some models. The units need both VOR and DME signals to operate in any RNAV mode. If the nav aid selected is a VOR without DME, RNAV mode will not function. In the VOR, or non-RNAV mode, the unit simply functions as a VOR receiver with DME capability. The unit's display on the VOR indicator is conventional in all respects. For operation on established airways or any other ordinary VOR navigation, the VOR mode is used. To utilize the unit's RNAV capability, the pilot selects and establishes a waypoint or series of waypoints to define a course. To operate in any RNAV mode, the unit needs both radial and distance signals. Therefore, a VORTAC or VOR DME needs to be selected as a nav aid. To establish a waypoint, a point somewhere within the service range of a VORTAC is defined on the basis of radial and distance. Once the waypoint is entered into the unit and the RNAV en route mode is selected, the CDI displays course guidance to the waypoint, not the original VORTAC. DME also displays distance to the waypoint. Many units have the capability to store several waypoints, allowing them to be programmed prior to flight if desired and called up in flight. RNAV waypoints are entered into the unit in magnetic bearings, radials, of degrees and tenths, and distances in nautical miles and tenths. When plotting RNAV waypoints on an aeronautical chart, pilots find it difficult to measure to that level of accuracy, and in practical application it's rarely necessary. A number of flight planning publications publish airport coordinates and waypoints with this precision, and the unit accepts those figures. There is a subtle but important difference in CDI operation and display in the RNAV modes. In the RNAV modes, course deviation is displayed in terms of linear deviation. In the RNAV en route mode, maximum deflection of the CDI typically represents 5 nautical miles on either side of the selected course, without regard to distance from the waypoint. In the RNAV approach mode, maximum deflection of the CDI typically represents 1 1/4 nautical mile on either side of the selected course. There is no increase in CDI sensitivity as the aircraft approaches a waypoint in RNAV mode. Confusion is possible when navigating an aircraft with VOR DME-based RNAV, and it is essential that the pilot become familiar with the equipment installed. It is not unknown for pilots to operate inadvertently in one of the RNAV modes, when the operation was not intended, by overlooking switch positions or annunciators. The reverse has also occurred with a pilot neglecting to place the unit into one of the RNAV modes by overlooking switch positions or annunciators. As always, the prudent pilot is not only familiar with the equipment used, but never places complete reliance in just one method of navigation when others are available for cross-check. Automatic Direction Finder, ADF. Many general aviation type aircraft are equipped with ADF radio receiving equipment. To navigate using the ADF, the pilot tunes the receiving equipment to a ground station known as a non-directional radio beacon, NDB. The NDB stations normally operate in a low or medium frequency band of 200 to 415 kHz. The frequencies are readily available on aeronautical charts or in the AFD. All radio beacons except compass locators transmit a continuous 3-letter identification in code, except during voice transmissions. A compass locator, which is associated with an instrument landing system, transmits a 2-letter identification. Standard broadcast stations can also be used in conjunction with ADF. Positive identification of all radio stations is extremely important, and this is particularly true when using standard broadcast stations for navigation. NDBs have one advantage over the VOR. This advantage is that low or medium frequencies are not affected by line of sight. The signals follow the curvature of the Earth. Therefore, if the aircraft is within the range of the station, the signals can be received regardless of altitude. This table gives the class of NDB stations, their power, and usable range. One of the disadvantages that should be considered when using low frequency, LF, for navigation is that low-frequency signals are very susceptible to electrical disturbances such as lightning. These disturbances create excessive static, needle deviations, and signal fades. There may be interference from different stations. Pilots should know the conditions under which these disturbances can occur so they can be more alert to possible interference when using the ADF. Basically, the ADF aircraft equipment consists of a tuner, which is used to set the desired station frequency, and the navigational display. The navigational display consists of a dial upon which the azimuth is printed, and a needle which rotates around the dial and points to the station to which the receiver is tuned. Some of the ADF dials can be rotated to align the azimuth with the aircraft heading. Others are fixed, with 0 degrees representing the nose of the aircraft and 180 degrees representing the tail. Only the fixed azimuth dial is discussed in this tutorial. This figure illustrates terms that are used with the ADF and should be understood by the pilot. To determine the magnetic bearing from the station, 180 degrees is added to or subtracted from the magnetic bearing to the station. This is the reciprocal bearing and is used when plotting position fixes. Keep in mind that the needle of fixed azimuth points to the station in relation to the nose of the aircraft. If the needle is deflected 30 degrees to the left for a relative bearing of 330 degrees, this means that the station is located 30 degrees left. If the aircraft is turned left 30 degrees, the needle moves to the right 30 degrees and indicates a relative bearing of 0 degrees, or the aircraft is pointing toward the station. If the pilot continues flight toward the station keeping the needle on 0 degrees, the procedure is called homing to the station. If a crosswind exists, the ADF needle continues to drift away from 0. To keep the needle on 0, the aircraft must be turned slightly, resulting in a curved flight path to the station. Homing to the station is a common procedure, but results in drifting downwind, thus lengthening the distance to the station. Tracking to the station requires correcting for wind drift and results in maintaining flight along a straight track or bearing to the station. When the wind drift correction is established, the ADF needle indicates the amount of correction to the right or left. For instance, if the magnetic bearing to the station is 340 degrees, a correction for a left crosswind would result in a magnetic heading of 330 degrees, and the ADF needle would indicate 10 degrees to the right, or a relative bearing of 010 degrees. When tracking away from the station, wind corrections are made similar to tracking to the station, but the ADF needle points toward the tail of the aircraft, or the 180-degree position on the azimuth dial. Attempting to keep the ADF needle on the 180-degree position during winds results in the aircraft flying a curved flight, leading further and further from the desired track. To correct for wind when tracking outbound, correction should be made in the direction opposite of that in which the needle is pointing. Although the ADF is not as popular as the VOR for radio navigation, with proper precautions and intelligent use, the ADF can be a valuable aid to navigation. Global Positioning System. The GPS is a satellite-based radio navigation system. Its RNAV guidance is worldwide in scope. There are no symbols for GPS on aeronautical charts, as it is a space-based system with global coverage. Development of the system is underway so that GPS is capable of providing the primary means of electronic navigation. Portable and yoke-mounted units are proving to be very popular, in addition to those permanently installed in the aircraft. Extensive navigation databases are common features in aircraft GPS receivers. The GPS navigation system broadcasts a signal that is used by receivers to determine precise position anywhere in the world. The receiver tracks multiple satellites and determines a pseudo-range measurement to determine the user location. A minimum of 4 satellites is necessary to establish an accurate three-dimensional position. The Department of Defense, DoD, is responsible for operating the GPS satellite constellation and monitors the GPS satellites to ensure proper operation. The GPS receiver verifies the integrity, usability of the signals received from the GPS constellation through Receiver Autonomous Integrity Monitoring, RAIM, to determine if a satellite is providing corrupted information. At least one satellite, in addition to those required for navigation, must be in view for the receiver to perform the RAIM function. Thus, RAIM needs a minimum of 5 satellites in view, or 4 satellites and a barometric altimeter, baro aiding, to detect an integrity anomaly. RAIM messages vary somewhat between receivers. However, generally there are 2 types. One type indicates that there are not enough satellites available to provide RAIM integrity monitoring, and another type indicates that the RAIM integrity monitor has detected a potential error that exceeds the limit for the current phase of flight. Without RAIM capability, the pilot has no assurance of the accuracy of the GPS position. GPS navigation has become a great asset to VFR pilots, providing increased navigation capability and enhanced situational awareness, while reducing operating costs due to the greater ease in flying direct routes. While GPS has many benefits to the VFR pilot, care must be exercised to ensure that system capabilities are not exceeded. Types of receivers used for GPS navigation under VFR are varied, from a full IFR installation being used to support a VFR flight, to a VFR-only installation in either a VFR or IFR-capable aircraft. The limitations of each type of receiver installation or use must be understood by the pilot to avoid misusing navigation information. In all cases, VFR pilots should never rely solely on one system of navigation. GPS navigation must be integrated with other forms of electronic navigation, as well as pilotage and dead reckoning. Only through the integration of these techniques can the VFR pilot ensure accuracy in navigation. Always check to see if the unit has RAIM capability. If no RAIM capability exists, Be suspicious of a GPS-displayed position when any disagreement exists with the position derived from other radio navigation systems, pilotage, or dead reckoning. Check the currency of the database, if any. If expired, update the database using the current revision. If an update of an expired database is not possible, disregard any moving map display of airspace for critical navigation decisions. Be aware that named waypoints may no longer exist or may have been relocated since the database expired. At a minimum, the waypoints planned to be used should be checked against a current official source, such as the AFD or a sectional aeronautical chart. In summary, be careful not to rely on GPS to solve all VFR navigational problems. Unless an IFR receiver is installed in accordance with IFR requirements, no standard of accuracy or integrity has been assured. While the practicality of GPS is compelling, the fact remains that only the pilot can navigate the aircraft, and GPS is just one of the pilot's tools to do the job. VFR waypoints provide VFR pilots with a supplementary tool to assist with position awareness while navigating visually in aircraft equipped with area navigation receivers. VFR waypoints should be used as a tool to supplement current navigation procedures. The uses of VFR waypoints include providing navigational aids for pilots unfamiliar with an area, waypoint definition of existing reporting points, enhanced navigation in and around Class B and Class C airspace, and enhanced navigation around special use airspace. VFR pilots should rely on appropriate and current aeronautical charts published specifically for visual navigation. VFR waypoint names, for computer entry and flight plans, consist of 5 letters beginning with the letters VP and are retrievable from navigation databases. The VFR waypoint names are not intended to be pronounceable, and they are not for use in ATC communications. On VFR charts, a standalone VFR waypoint is portrayed using the same 4-point star symbol used for IFR waypoints. A VFR waypoint co-located with a visual checkpoint on the chart is identified by a small magenta flag symbol. A VFR waypoint co-located with a visual checkpoint is pronounceable based on the name of the visual checkpoint and may be used for ATC communications. Each VFR waypoint name appears in parentheses adjacent to the geographic location on the chart. Latitude-longitude data for all established VFR waypoints may be found in the appropriate regional AFD. When filing VFR flight plans, use the 5-letter identifier as a waypoint in the route of flight section, if there is an intended course change at that point, or if used to describe the planned route of flight. This VFR filing would be similar to VOR use in a route of flight. Pilots must use the VFR waypoints only when operating under VFR conditions. Any VFR waypoints intended for use during a flight should be loaded into the receiver while on the ground and prior to departure. Once airborne, pilots should avoid programming routes or VFR waypoint chains into their receivers. Pilots should be especially vigilant for other traffic while operating near VFR waypoints. The same effort to see and avoid other aircraft near VFR waypoints is necessary, as is the case when operating near VORs and NDBs. In fact, the increased accuracy of navigation through the use of GPS demands even greater vigilance, as off-course deviations among different pilots and receivers is less. When operating near a VFR waypoint, use whatever ATC services are available, even if outside a class of airspace where communications are required. Regardless of the class of airspace, monitor the available ATC frequency closely for information on other aircraft operating in the vicinity. It is also a good idea to turn on landing lights when operating near a VFR waypoint to make the aircraft more conspicuous to other pilots, especially when visibility is reduced. Lost procedures. Getting lost in an aircraft is a potentially dangerous situation, especially when low on fuel. If a pilot becomes lost, there are some good common sense procedures to follow. If a town or city cannot be seen, the first thing to do is climb, being mindful of traffic and weather conditions. An increase in altitude increases radio and navigation reception range and also increases radar coverage. If flying near a town or city, it might be possible to read the name of the town on a water tower. If the aircraft has a navigational radio, such as a VOR or ADF receiver, it can be possible to determine position by plotting an azimuth from 2 or more navigational facilities. If GPS is installed, or a pilot has a portable aviation GPS on board, it can be used to determine the position and the location of the nearest airport. Communicate with any available facility using frequencies shown on the sectional chart. If contact is made with a controller, radar vectors may be offered. Other facilities may offer direction-finding assistance. To use this procedure, the controller requests the pilot to hold down the transmit button for a few seconds and then release it. The controller may ask the pilot to change directions a few times and repeat the transmit procedure. This gives the controller enough information to plot the aircraft position and then give vectors to a suitable landing site. If the situation becomes threatening, transmit the situation on the emergency frequency 121.5 MHz and set the transponder to 7700. Most facilities and even airliners monitor the emergency frequency. Flight diversion. There probably comes a time when a pilot is not able to make it to the planned destination. This can be the result of unpredicted weather conditions, a system malfunction, or poor pre-flight planning. In any case, the pilot needs to be able to safely and efficiently divert to an alternate destination. Before any cross-country flight, check the charts for airports or suitable landing areas along or near the route of flight. Also, check for navigational aids that can be used during a diversion. Computing course, time, speed, and distance information in flight requires the same computations used during pre-flight planning. However, because of the limited flight deck space, and because attention must be divided between flying the aircraft, making calculations, and scanning for other aircraft, take advantage of all possible shortcuts and rule-of-thumb computations. When in flight, it is rarely practical to actually plot a course on a sectional chart and mark checkpoints and distances. Furthermore, because an alternate airport is usually not very far from your original course, actual plotting is seldom necessary. A course to an alternate can be measured accurately with a protractor or plotter, but can also be measured with reasonable accuracy using a straight edge and the compass rose depicted around VOR stations. This approximation can be made on the basis of a radial from a nearby VOR or an airway that closely parallels the course to your alternate. However, remember that the magnetic heading associated with a VOR radial or printed airway is outbound from the station. To find the course to the station, it may be necessary to determine the reciprocal of that heading. It is typically easier to navigate to an alternate airport that has a VOR or NDB facility on the field. After selecting the most appropriate alternate, approximate the magnetic course to the alternate using a compass rose or airway on the sectional chart. If time permits, try to start the diversion over a prominent ground feature. However, in an emergency, divert promptly toward your alternate. Attempting to complete all plotting, measuring, and computations involved before diverting to the alternate may only aggravate an actual emergency. Once established on course, note the time and then use the winds aloft nearest to your diversion point to calculate a heading and ground speed. Once a GS has been calculated, determine a new arrival time and fuel consumption. Give priority to flying the aircraft while dividing attention between navigation and planning. When determining an altitude to use while diverting, consider cloud heights, winds, terrain, and radio reception. This tutorial has discussed the fundamentals of VFR navigation. Beginning with an introduction to the charts that can be used for navigation, to the more technically advanced concept of GPS, there is one aspect of navigation that remains the same. The pilot is responsible for proper planning and the execution of that planning to ensure a safe flight. This concludes your introduction to navigation. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.